Hey guys, today we are looking at 4.5 day 2, which is all about rational root theorem. We're actually going to take a look at three different theorems today, our factor theorem, our rational root theorem, and then our complex conjugate theorem. So a lot of information. Let's go ahead and jump right in. So our first one is an alternative way to check and see if something is a factor. I know back in the first part of chapter 4 we talked about how one way of checking to see if it's a factor besides just factoring it out would be doing synthetic division on a certain thing, right, a factor, to see if that worked and gave me a remainder of 0. Or if I have a remainder of 0, that means it factors perfectly with nothing left over. So that's one way of checking it. Another way of looking at it is if you have a factor, so x minus a being just a linear factor, that a value, when you plug that into the function itself, should give you a 0 back out. Which makes sense, because if we remember box 3 of yesterday's notes, finding the zeros of a function was the same thing as finding the solutions to that equation. So of course, if it's a solution, it's going to be a factor. We're kind of working backwards. So I prefer doing it the synthetic way just because with the complex equations that we're going to be dealing with, the math itself is easier to do mental math with synthetic division. But this is an option for you as well. If you're checking to see if something is a factor, you could just plug it into the function and check to see if it's 0. Obviously, if you get your calculator handy and you're pretty good typing stuff in, even with complex stuff, that's a perfectly viable option. I will show you the synthetic division route as I go through the rest of these notes. Okay, so that's the factor theorem. Kind of just putting it in there, making that statement, and we can kind of choose how we want to use it. The next one is what most of our notes are going to be focused on today, at least the good first half of the notes, is something called rational root theorem. And this is a way or a tool that we can use to be able to identify possibilities for factors of our function if there's no possibility of factoring it out using any of the tools we know how to use so far. So if it's not factorable using regular old school factoring, Xbox factoring, factor by grouping, any of the special shortcuts we know, if none of that's working for us, and it's not just a quadratic we could use quadratic formula on, we kind of are at a loss. We're going to have to start guessing different things, different factors, different solutions, and doing synthetic or this factor theorem to try and see which one happens to work for us, and then we can kind of go from there. So instead of going just off of this huge long list of all of the possibilities, every number in existence, just start guessing stuff, they, old mathematicians and people who used to have no way of entertaining themselves other than playing with numbers, have figured out this relationship where if you're trying to factor something, so if we want to look up here, I'm just going to use this scratch space up here. If we had something like x squared minus 5x plus 4 equals 0. If we were going to factor that using the tools we know how to, that factors out into, what is that, x minus 1, x minus 4 equals 0. So our two solutions are positive 1 and positive 4. And they looked at all of these different possibilities, all these different things that factored, and found this pattern where the solutions that we had, which is to say the factors that we had, were all factors of both my lead coefficient and my constant. Those two things, kind of those end caps, the first term and the last term, are what determines what those different possibilities are for real roots. So they realize that it happens not just, they have to be factors of those two things, but in a very specific relationship where this right here, P over Q, P is the factors of the constant, and Q are all factors of the lead coefficient. So if you identify what those things are, if you know what the lead coefficient is, if you know what the constant is, if you take the factors of those, all of the possibilities that we have are just those two things. So we start with a list of numbers for my lead coefficient factors, my constant factors. I can put them in that relationship of P over Q in order to get my list of all the possibilities that we have for rational roots. So that's not, in some cases, depending on what the factors are and what the numbers are that we're dealing with, it could still be a really long list, but at least it's a smaller list than all the possible numbers that are out there in the real world. So again, that's just a way for us to narrow it down. So I got an example down here if you want to use. This is just kind of exploring the definition a little bit more. So A being my lead coefficient and Z being my constant, right? My lead coefficient is the number that's attached to the highest degree term. My constant is the number that does not have a variable attached to it, right? It's x to the 0 power. All the factors of A give me my p-value, that's my denominator. So the factors of my lead coefficient are my denominator. And then my factors of the constant, which in this case are Z, are all of my my p-values, which are up top. So it's a whole lot easier to wrap your head around as soon as we start seeing some examples. So let's go ahead and just jump down in here into example number 1. So example number 1, our function is f of x equals x cubed plus x squared minus 8x minus 12. And again, if we looked at this, if we tried factoring this using the tools that we know, kind of what I would think first would be, since there's 4 terms, would be factor by grouping. I do have GCFs between the things the first 2 and the last 2. But if I tried factor by grouping, we would see that those parentheses that I want to be the same in order to do factor by grouping, it doesn't work. So I can't do factor by grouping here. It just is not going to fit. So I have to then try some other method. And we don't have any other method of factoring a 4-termed polynomial other than factor by grouping. So that's why we'll go ahead to kind of start with a smaller list of numbers to work off of and then start just guessing at some to see if they're factors or not. So first things first, we have to identify what's my lead coefficient and what's my constant. So in this case, my lead coefficient is just a positive 1 because that's just an x cubed out in front. My constant is negative 12. So that's my constant. So if I'm looking at just factors of those things, well, factors of 1 are easy. It's just going to be positive or negative 1, right? Negative 1 times negative 1 is 1. Positive 1 times positive 1 is 1. So that's my only 2 factors of 1 are 1 and negative 1. Now my factors of 12 is a little bit of a longer list. You've got 1 times 12. You've got 2 times 6. And you've got 3 times 4. Those are all the numbers themselves. And all of these, I can just tell you now, because we can do a positive times a positive or a negative times a negative to get positive numbers. Or, in this case, since I'm looking for a negative 12, I could say it's a positive 1 times a negative 12, and then a negative 1 times a positive 12. You're going to have plus or minus in front of all of these. So whether or not you want to remember to write that for each individual one, or if you want to just say plus or minus for all of them and just know that it's both positive or negatives that are possible, that's our list of numbers. So in this case, if those are my factors of my constant and my factors of my lead coefficient, since they always, my possible rational roots are always p over q, factors of my constant over the factors of my leading coefficient, in this case, it's a pretty easy list because all I'm doing is taking these factors of my constant, 1, 2, 3, 4, 6, 12, and just dividing it by positive negative 1. So I end up with plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 4 over 1, plus or minus 6 over 1, and then plus or minus 12 over 1, which we realize is really just the list of those factors of my constant, because dividing by 1 is not going to make any difference. So that gives me my list of factors to start with. These are my possibilities for my roots. And again, like I said, I understand it's a long list. It's 1, 2, 3, 4, 5, 6, so 12 different possibilities. But 12 is a whole lot better than an infinite number of possibilities to start plucking from to try and figure out which ones work and which ones don't. So from here, we're going to just pick out some numbers and just start testing them, checking to see if they're a factor, meaning either use synthetic to see if it has a remainder of 0, or you could use that new factor theorem where you take some of these numbers, plug them in to see if they work in my, if they give me 0 when I plug it into the function. Those are my 2 different possibilities. I prefer synthetic, so I just start picking out some of these numbers to use for synthetic division. And this part can be tedious and time consuming. It really kind of depends on how good of a guesser you are. For the life of me, I can't really I don't have a rhyme or reason to numbers that I pick. I usually try and pick things more in the middle, but that's just my personal preference. There's not really, I mean, you've got a whole number of possibilities where it's going to be. I always start with nice numbers. Here, all of my numbers are nice, so I'm just going to pick something. I'm going to just say, let's test to see if 4 works in synthetic. And remember, for synthetic division, since I'm dividing, I'll scoot it back up down there, or scoot it back down up there. X cubed plus x squared minus 8x minus 12. To set up synthetic, I just put my coefficients here. So 1x cubed, 1x squared, negative 8x, negative 12. And then I just kind of, I'm going to switch to red. I drop this down. Hey, it's still a 1. 4 times 1 is 4. Add those up, gets 5. 4 times 5 is 20. Adds up to 12. 4 times 12 is 48. And all we care about is that it is not 0. It doesn't matter what the number is, as long as it's not 0. That tells me 4 does not work. 4 is not a factor. So we move down the list. You can either try negative 4, you could try a different one. I like to try and stay positive just to, they're usually easier to work with. Let's just go next down the list and let's say 3. 3 is still kind of in the middle of the list. 1, 1, negative 8, negative 12. And again, we're just doing the same process over again till we hit something that has a remainder of 0, because that means that that is a factor. So 3 times 1 gives me 3, which adds up to 4. 3 times 4 is 12, which adds up to 4. 3 times 4 is 12, which adds up to 0. And yay, we found the first one. So we know that 3 works, which, if we remember how synthetic works, if 3, my number up here in the box, is a factor, or is my R value, this really means that x minus 3 is that factor, right? It's always the opposite in that little box. And the same thing does apply if we're using that that factor theorem that we talked about up above. If 2 works when you plug it in there, that means x minus 2 is the factor. So same idea here. Now what I'm left with, this 1, 4, 4, and then my 0 is my remainder, that's what it factors out into for the leftovers. X minus 3 is that first factor, and then 1x squared plus 4x plus 4 is what the other stuff is, right? X minus 3 times that gets me back to my original. And now after you do this the first time, you should be able to factor what's left over. There's going to be very rare occurrences where you have to do synthetic more than once to identify another factor. So from here, I'm just going to factor completely. So now my x minus 3 is not going to change, but here this other parenthesis factors out into x plus 2 times x plus 2. So those are my 3 factors. Really, 2 factors, two solutions, one of which is has multiplicity of 2. All right, we're going to do a couple more examples of these just so you guys get a feel for them. Again, we are starting with factors of my lead coefficient, which in this case is now 3, factors of my constant, which is negative 2. So much fewer, far fewer factors to deal with. We've got plus or minus 1 and plus or minus 3 for my leading coefficient. And then factors of negative 2 would be plus or minus 1 and plus or minus 2. Again, those plus or minuses will always be there. It's really looking at what numbers will multiply together to give me those numbers that I'm trying to factor out. So now what I have to do is, because my factors, my possible roots, are always P over Q, which is, again, factors of my, constant over my coefficients, right? So I have to make sure every possible combination is represented. So one possibility would be taking my factors of my constant over 1, so plus or minus 1 over 1, plus or minus 2 over 1. But then we also have the possibility of having some uglier stuff with plus or minus 1 over 3 and plus or minus 2 over 3. So those are my 8 different possibilities, either positive negative 1, positive negative 2, positive or negative 1/3, or positive or negative 2/3. Those are my different possibilities. I've got all 4 of those options. So now you're going to test them out. And again, this is where I'm saying it's up to you which ones you test out. I always start with the nicest ones. So I would try all 4 whole numbers first. I would try positive 1, negative 1, positive 2, negative 2 before I have to move on to one of those fractions, just to make it easy on yourselves. Because again, once you get that first one, you should be able to factor out from there. So from here, we've got, I don't know, let's just try negative 2, I guess, or positive, doesn't really matter. Let's just try negative 2. I started with a positive one before. Let's try a negative one, see if that works out for us. So we've got 3x cubed minus 2x squared minus 7x minus 2. All right, so drop it down. 3, negative 2 times 3 is negative 6, which adds up to negative 8, which is positive 16, which is positive 9, which is negative 18, which is negative 20. So negative 2 ain't it, Chief. It's not going to work. Let's try positive. Let's see if that's going to work for us. We try out positive 2 instead. Still 3, negative 2, negative 7, negative 2. Drop it down. 3 times that is 6, which adds up to 4, which is 8, which is 1, which is 2, which is 0. So yay! 2 is my first one that works. Obviously, I pre-planned it. I wanted to see one that didn't work, but it might be something where you have to do 2 or 3 of them before you get the first one that does. Maybe you're just a golden god and you guess the first one and it happens to be a remainder of 0 and you're just awesome. I hope that that's the case for all of them. But again, I still have to factor completely. So since 2 worked as my number inside synthetic, x minus 2 is one of my factors. And then here I've got 3, 4, 1, which means 3x squared plus 4x plus 1. Now this is factorable. We'll do some Xbox factoring to get this to factor out. You could, if you really wanted to, you could repeat the process over again to use this new polynomial, this 3x squared plus 4x plus 1. That would still work with my rational roots. I could still say, all right, factors of 1 over factors of 3 to try and guess and check and do synthetic again if that's easier for you. But we're pretty good at Xbox factoring, right? We'll do a quick little recap of that to remind ourselves of how we would handle that. Again, for our box, for Xbox factoring is always our first term and our last term there and there. Our top comes from our first times our last, so 3 times 1. Our bottom comes from our middle, which is a 4. So we're trying to figure out what 2 numbers multiply together to give me 3, but add up to 4. In this case, pretty easy to see it's 3 and 1, which means 3x and x are those numbers there. So as I go through and do my GCFs, 3x squared and 3x have a 3x in common, which means this has to be x, this has to be 1, this has to be 1. So my final factorization, x minus 2, 3x plus 1, x plus 1. And if you actually solved those, all 3 of those are in my original list. This first parenthesis is a 2, 2 is in my list. The middle parenthesis, negative 1/3, was in my list. My last one, negative 1, also in my list. All 3 of those would have been ones that work out with synthetic to give me a remainder of 0 if I tested it. It is what it is. All right, last example of this style. This one quite a bit more complicated just because it's just a much, much longer process. So still the same setup. I'm still looking at my lead coefficients versus my constants. So my factors of my lead coefficient of 1 are just positive and negative 1, which is nice. My factors of my constant are it's a little bit longer of a list because 36 there's a lot of even numbers that multiply into it. So all of these are going to be plus or minus. I'm just not going to rewrite it every single time. We've got 1 times 36, 2 times 18, 3 times 12, 4 times 9, and then 6 times 6. So all of those are possibilities, and obviously all of those will be both positive and negative. So huge list to work off of here. So I'm not going to rewrite it. It's just going to be this same thing is my possible roots, because it's all over positive, negative 1. So we're just going to start guessing some. Let's just start with, I like to start towards the middle of my list. So let's just say we'll start at like positive 4 maybe. If we try positive 4, trying to factor out 1x to the 4th, minus 3x cubed plus 5x squared minus 27x minus 36. So going through synthetic, drop my first term as a 1. 4 times 1 is 4, which adds up to 1. Still multiplies by 4 is a 9. That's a 36, which is a 9 again. 4 times 9 is 36, which adds up to 0. So hey, 4 is my first one. So x minus 4 times what was left over here. I'll rewrite this in blue, that's what I've been doing. X minus 4, and then I was left with 1. Now this is going to be x cubed plus x squared plus 9x plus 9. So at this point, it's up to you on how you want to continue. Now that parenthesis I'm left with there is factorable using factor by grouping, so we could go that route if we wanted to, or if you want to, you could repeat this process over again with just this aspect, just the x cubed plus x squared plus 9x plus 9. So you would look at just factors of 9 over 1, and then look and just see which ones work out there. You can kind of eliminate some of those ones from the original list that aren't also factors of 9. Or we could do factor by grouping, which I'll show you kind of both of those. If I go, we'll say green for grouping, if I wanted to factor this by grouping, x cubed plus x squared plus 9x plus 9. I'm going to factor those out. I'm going to group those up together just as they are. 9x plus 9. They've got x squared in common here. Leaves me with x plus 1. They've got a 9 in common. That leaves me with x plus 1. So we've got x plus 1, x squared plus 9 is what that factors out into. And of course, this x minus 4 is still a factor. Now be careful that x squared plus 9 does not factor any further. X squared minus 9 would factor further, but it's not it's not factorable any further than that. It's x squared plus 9 and x squared minus 9. Now here my instructions are to factor. Sometimes, and I'm going to switch over to, that was green, so let's do red. Sometimes they will ask you to solve the equation. So in this example number 3, if they said, find the zeros of this or solve this equation, that could be an instruction instead of just factor completely. If that was the case, you would just go ahead, just like we usually do, just set each of those parentheses equal to each other. X minus 4 equals 0, x plus 1 equals 0, and then x squared plus 9 equals 0. So this gives me an x equals a positive 4. This gives me x equals a negative 1. This one, x squared equals negative 9. So when I square root both sides, x equals plus or minus 3i. If we go back to that stuff that we looked at last semester. Remember your eyes? Yeah, they're about to come back for us. This kind of, the way that we do this is obviously, that would be your solutions. Totally fine to just leave it like that. But this leads nicely into our next thing that we're talking about here, because if you notice here, my real numbers could just be single solutions, but my imaginary numbers, my complex ones, they always come in pairs, right? It's always, we never got anything where we got, an I in my answer and it was just positive 3i or negative 3i. It was always plus or minus, because those i's only ever happen when we're dealing with square roots, and those always come in plus or minuses when we're solving the equation. Same thing with solving using square root method, those were always coming in plus or minus form, right? It was never x equals 2 because I took the square root. I've always got that plus or minus that happens. That's really what the next theorem that we're talking about kind of goes back to. The conjugate root theorem tells me that anytime I deal with a complex number, so it could be a complex number dealing with an irrational, so a square root that does not simplify, or it could be dealing with an imaginary number, they always are going to be coming in pairs because of that plus or minus relationship there. So irrational roots always come in pairs. I'm going to switch back to blue. They always come in pairs of conjugates because, again, of that plus or minus relationship. So if I have a plus b square root of b, I also have a minus the square root of b. So that means if I know 6 plus the square root of 3 is a solution, then 6 minus the square root of 3 also has to be a solution. Or if negative square root of 5 is a solution, positive square root of 5 is a solution. The same thing happens with our complex roots, so our imaginaries, because we know that I represents the square root of 1, so it's really the same thing, still dealing with square roots. They also come in pairs. And again, same pattern here. If a plus bi is a solution, then a minus 3bi has to also be a solution. So here, 5 minus 7i tells me that 5 plus 7i is also a solution. Or if 3i is a solution, negative 3i has to be a solution. So they always come in pairs when they're complex, just to kind of, round out nicely, because they never are a single thing because of that square root relationship. So some of the problems you might be asked to do are just identifying all of the given roots. So if I'm given some roots, and they're asking us in this case to find 2 additional roots that were given. So looking at part A, 2 over 5, that is just, it's not complex. There's no square root to it. There's no imaginary i's to it. So that one doesn't tell me anything in addition. But these 2 solutions, these 2 roots, are complex or irrational. So I can identify 2 more from that. So 3 minus the square root of 7 is also a root. And then positive 4i also has to be a root. Those would be 2 additional ones that I have there. Same thing with part B here. 4 plus 7i tells me 4 minus 7i has to be a solution. If negative square root of 17 is a root, positive square root of 17 has to also be a root. Pretty straightforward stuff for identifying roots. Now, the second big skill that we'll deal with in this section is working backwards. So we've dealt with identifying roots and finding solutions and factoring from a function that we're starting with, or an equation that we're starting with. We are also going to be asked to work backwards. So if I give you the roots, or if we are given the roots, or if we're given the zeros, or whatever the case may be, however they phrase it, we have to be able to write the equation from that thing. So the nice thing is it's a pretty straightforward process. We know from what we started with in the very first definition of this set of notes, if x minus a is a factor, that means a is a solution. A has to be my root. So what I can do is work backwards. If I'm given my roots, x minus that number has to be a factor, and then we'll just multiply stuff out like we did back in, who even knows, back in Algebra 1. So in this case for part A, if 7 and negative 10 are my two roots, that tells me x minus 7 and x minus negative 10 have to be my 2 factors, which really we know that means x minus 7 and x plus 10 are my 2 factors. So from there, it's just foiling, right? X times 10, negative 7 times x, negative 7 times 10. So we get x squared plus 3x minus 70. That's it. Pretty straightforward, right? Super easy when they're all real. Where it gets to be complex, see what I did there? Is where we start having those irrational roots, or we have those complex roots. So in this, if I'm given a root that is complex or irrational, where it should come in conjugates, but I'm not given both of them, you have to start by identifying that other one. So in this case, if For part B, we were given that 5i is a factor, is a root, so that means negative 5i is also a root. So in dealing with that, that means x minus 5i times x plus 5i would be my two factors, right, my two linear factors. So now I have to FOIL that out. I have to multiply those together. So still the same process. I'm still just foiling. So x times x times 5i, negative 5i times x, and then negative 5i times positive 5i. So that gives me an x squared, positive 5ix, negative 5ix, and then negative 25i squared. So as I FOIL this out, my 5ix and negative 5ix, those are going to cancel out. We should remember from last semester that I squared is the same thing as negative 1. So really this turns into x squared for my first term minus 25 times negative 1, which negative 25 times negative 1 ends up just being x squared plus 25. Now, the nice thing is, as complex and as weird as that is, there's a pattern that develops. You'll kind of notice where this, anytime we had like a 5i and negative 5i, it basically turned into the sum of two cubes. That's always going to be the case. So you see here, I started with 5i and negative 5i. I just ended up with x squared plus 25. That's always going to be the case. If you have 3i and negative 3i, it's going to turn into x squared plus 9. So you can kind of see those patterns, and it gets a little bit easier. All right, so C, we have two different complex conjugates that we'll have to deal with. So if we know that x minus the square root of 5 is a factor, x plus the square root of 5 has to be a factor, x minus 4i and x plus 4i. So the other thing we could kind of take advantage of here is the fact that they're both the difference of two squares. So if you want to kind of skip that foiling process, we can identify this first pair, right, as the difference of two squares, where this is just going to be x squared minus square root of 5 squared. And then my second set of parentheses, this right here, is going to be x squared minus 4i squared. And you kind of go that way. It's another way of handling it, right? Taking a look at it. So this ends up being x squared minus 5, right? Because the square root of a square, or a square of a square root is just whatever's underneath it. And then here we've got x squared minus 16i squared. So again, that negative 1 gets replaced for my I squared, and this ends up being x squared minus 5 times x squared plus 16. Unfortunately, from that point, we do have to kind of go the more old school method and FOIL that out. So first times first is x to the fourth. Outsides would be x, so 16x squared. Insides would be negative 5x squared. And then lasts, what is negative 5 times 16? Negative 80. So I collect up my like terms, x to the fourth plus 11x squared minus 80. Not very pretty. Not at all. All right, so for the last one, for E, we've got something super ugly, because even though we've got two numbers here, this is still just a single factor, right? 3 plus 2i is one of my roots, and so that means that 3 minus 2i is another one of my roots, but those aren't when I multiply together. Remember, these are still my roots, so I still have x minus 3 plus 2i, and then I have x minus 3 minus 2i. So if I kind of distribute my negative here, I've really got x minus 3 minus 2i times x minus 3 plus 2i. And I have to multiply that together. And even though each of those individual terms are super straightforward and simple, I have three different terms. I have a trinomial times a trinomial. Probably going to be easiest for us if we go ahead and just use box multiplication. So I'm going to go ahead and just set up a 3x3 grid for us to be able to use. So I've got, switch to green here for the actual numbers, x, -3, -2i, x, -3, +2i. So that's x squared minus 3x minus 2ix. This is -3x. This is 2ix. -3 times -3 is 9. -2i times -3 is a +6i. -3 times a +2i is a -6i. And then -2i times 2i is a -4i squared. So we've got common denominators there and there. Common denominators there and there. I guess common like terms here and here. And then this last box down here, my I squared we know is -1, so really this is -4 times -1, so it's a +4. So I actually have a like term here and here as well. Super complicated, which is just so much fun. So in total, we've got x squared minus 6x. If you notice these two in blue, +2ix and -2ix, they just cancel each other out. My -6i and my +6i, once again, those just cancel each other out. 4 and 9 adds up to 13. So super messy, but a very simple quadratic. So that would be what that factors out into. I know this is a super long set of notes, so we're actually going to kind of push this off a little bit. I know originally I told you tomorrow, Wednesday, would be our practice day for 4.5. I'm just going to let you guys get a little bit caught up because I know most of yesterday was spent working on the notes for day 1. All of this class period has been spent working on watching the video for this set of notes. So tomorrow, Wednesday, you guys will have time to get caught up on both sets of bookwork. And then Thursday will be our practice day for 4.5. I think I have it set up as a practice A worksheet. That'd be a puzzle time. I think it's a practice A worksheet. So yeah, that's all I got for you. The homework for this section is pretty small in terms of number of problems, but it's because most of it is from that last section, right, where you're given some factors and you have to identify what the original problem was that you started with. So there are going to be some tedious problems for some of them, but again, that's why I gave so few of them. But it is all, both evens and odds, so page 95, 41 to 46, all. As always, if you have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. And if not, have a fantastic day. We'll see you guys soon.